Good evening, dear participant, and welcome back to this 6-day session on advanced regression techniques of ongoing workshop on biostatistics from basic to advanced techniques, jointly organized by Methodic Thinking Foundation India and Baba Farid Group of Institution. Today in this session, our resource person will be Geethu Pal. She is biostatistician, Amrita Institute of Medical Science and Research Center, Kochi, India. So before inviting her, I would like to have a brief introduction about her. She is passionate and self-motivated biostatistician with a master's degree in biostatistics from the Indian Council of Medical Research, National Institute of Epidemiology, India. She specialized in applying advanced statistical method to real-world problems across various research fields. Geethu has hands-on experience in data management, meta-analysis, and spatial analysis, with the proficiency in statistical software such as R and SAS. Currently, she is working as research assistant at Amrita Institute of Medical Sciences and Research Center. She is dedicated to achieving high standard of excellence in applied statistics and is driven by commitment to research and professional growth. She has vast experience in statistical model, and I hope that the content which she will deliver and most of the content as we discuss are hands-on, and some database she has already shared with us, and all these are available in the WhatsApp group. And in the afternoon, we drop a message, please download this data set so that we can easily start. So that we can easily start this session. So now I would like to welcome our resource person, Geethu Paul. Over to you, ma'am. Now you can start. Also, dear participant, you are allowed to unmute your mic during the session. So whenever you feel you have any question, you can put directly. Okay. So just 1 minute, ma'am. Yes, ma'am. Now you can unmute your mic.
Hello. Hello, am I audible now?
Yes, ma'am. You are audible.
So can I start the session now?
Yes, ma'am. We should start now.
Okay. So thank you for the brief introduction about me. And today we'll be handling the advanced regression techniques, that is the multiple linear regression, logistic regression, and the model evaluation techniques. So now I'll share my screen. Please inform if it is clear.
Yes, ma'am. It's perfect clear.
Is it visible now?
Yeah, visible.
I think it is in the presentation mode, right?
Yeah, fine.
Okay. So by now, like the 5-day lectures will let us know what the statistics is from the basics to until the simple linear regression techniques. So you may be knowing the basics of a regression right now. So by this end of this lecture, you'll be able to perform a multiple linear regression analysis, and you may be able to conduct a logistic regression and also apply techniques for model evaluation and validation. So let us get into multiple linear regression, its introduction. So last day you will be dealing with simple linear regression, in which you have one independent variables and you got to know how that particular independent variable is associated with our dependent variable. Now the case changes if we have multiple independent variables. So this multiple linear regression is a statistical method that models the relationship between an dependent variable with two or more independent variables. So as you can see the equation here, so y is our dependent variable, and you have x1, x2, etc. up to xn, which are the independent variables, and you have certain coefficients associated with it. So beta naught here without an independent variable is the intercept of this regression equation, and beta 1, beta 2, etc. up to beta n constitutes the coefficients of each independent variable. So this particular value represents how much effect each independent variable is giving to the regression when other variables are present in our data. So in medical research, when we look upon this, multiple linear regression helps us to predict a patient outcome when he is dealing with multiple factors. So you can see a figure down, that is our dependent variable is blood pressure. Okay, so how this blood pressure is getting affected if multiple factors are getting an effect on it. So here it is age, weight, and medication dosage. So how does the blood pressure changes if the age is increasing? Is the weight increasing or decreasing? Or when we change the dosage of the medication, how does it impact on the blood pressure? So combined effect of all these variables, how this blood pressure changes. So this can be assessed using this multiple linear regression. So this will be our brief overview. So in order to conduct a multiple linear regression, there are certain assumptions. So here you can see 5 assumptions running around. That is existence, linearity, homoscedasticity, normality, and independence. So we can see one by one. So existence means if we have a particular independent variables, that is x1, x2, etc. up to xk, then there should exist a dependent variable y with the probability distribution. So for any combination of this particular independent variables, there should exist a particular value for y. And next one is independence, that is the y observations. The dependent variable observation should be statistically independent of each other. And linearity means since we are dealing with multiple linear regression, the combination of independent variables which we take should have a linear relationship with the mean value of y, which you will be heard before in the simple linear regression classes also. And the next comes is the homoscedasticity, which means for any combination of this independent variables, whether the variance of y is same. And the normality, as we know, the independent variables, the combination of the independent variables should have a particular dependent variable, and the dependent variable should follow a normal distribution. And also the residual values, the error values should also follow a normal distribution. So these are the 5 main assumptions of multiple linear regression, which will be checked before doing a multiple linear regression. So let's come to an example. So you are seeing a particular table in the right side, and it's systolic blood pressure, and there is a BMI of a patient. Then there is age. So we have 2 independent variables, and systolic blood pressure denoted by SBP will be our dependent variables. So giving this particular simple example, we need to see how this particular age and BMI is associated with systolic blood pressure. We need to know whether there is a change with increasing of age, increasing of BMI and all. And we have fitted a particular multiple linear model. As we see in the first slide, how we write the combination of independent variables to the dependent variable. So we see the systolic blood pressure is equal to 80 plus 0.6 age plus 2.5 BMI. So the intercept here is 80. Slope of the age is 0.6, slope of the BMI is 2.5. So apart from other sectors, when we are dealing with the medical research sector, the intercept value is like we cannot interpret directly an intercept value. For example, say intercept value is those value which gives the value of the dependent variable. Say for example, if the person's age is 0 and the BMI is 0, then the systolic blood pressure of that person is 80. This is how we interpret that particular intercept. But when we are dealing with a medical scenario, whether the person's age cannot be 0 or his BMI cannot be 0, that is not a valid case. So in that case, we'll have some values for age, some values for BMI. So the intercept gives the base value plus whatever age the person have, whatever BMI the person have, we add upon and we see what is the systolic blood pressure of that particular person. So we have I have given an interpretation for particularly one variable, that is age. So we see as 1 year of age increases, then the mean systolic blood pressure, that is the average change in the dependent variable, is expected to increase by 0.6 units. And we assume that all the variables other than the age is remaining constant. So say suppose here we have two variables, so we can interpret directly 0.6 and 2.5. Say we have multiple variables other than these two, we give a particular assumption that all other variables except the variable we are interpreting is remaining constant across. And we say that this is the average effect of that independent variable to the systolic blood pressure. This is how the interpretation goes. Now, we have fitted a model and we see that age and BMI have certain coefficients, and this is the effect of these particular variables to the systolic blood pressure. Now, once we have estimated the parameters in the model, we face two main questions. What is the overall adequacy that we have given to the model, and which regressors are important? Whether age is important, whether BMI is important, or none of them are important, we don't know. So we need to check whether they are important. So this leads to the hypothesis testing in this multiple linear regression. So coming to the hypothesis testing in multiple linear regression, we have mainly three main tests. So first one is that we have a collective information about certain variables. We have a set of n variables and we put on all the n variables to the model and we see whether this collective information is providing any impact on the dependent variable. So overall significance test is about that. It takes the entire set of independent variables and test. And next one is whether we are adding any other variable to the model, does the model become better? Or else we can add a certain group of variables and we see whether there is a difference. So we'll go one by one. So this is the test of significance for overall regression. So the null hypothesis for this model becomes, we have k independent variables and we are considering together. When we consider together, it is assumed that it does not explain a significant amount of variation in the dependent variable. So the null hypothesis will be like whatever a variable explains is being denoted by their beta coefficients. So we say all the beta coefficients is equal to 0, which means none of them are explaining anything. And the alternative hypothesis will be at least one among the beta is explaining, so that there is an effect of that particular variable to the dependent variables. So when we reject this particular null hypothesis, then it is being proven that at least one variable in the model contributes significantly to the better fit of the model. Now we need to test the hypothesis. You have been knowing how a particular variable is tested, how a group of variable is tested. And here we have a certain number of variables. So we use the F test and we computed the F statistic. So once the statistic is being computed, we will be comparing that F statistic with the critical value of that particular F, and then we see if the critical value, the computed value is greater than the critical value, we obviously reject this particular null hypothesis. So if we reject this null hypothesis, then we comes up the question that one variable is being contributing better to our model. So once the test for overall significant overall regression is being done, we determine that at least one of the regressors is important. So we need to know whether an additional variable, whether we include another variable where the model become more effective, or if deletion of any of the variables already in the model will give a better model. These were the two conditions which will come up to our mind once we fit an overall regression model. So Now here we have another test, that is a test for addition of another variable. So we have a full model. Full model will consist of all the independent variables, and we combine all the independent variables and we are seeing the effect of these independent variables to the dependent variable. So we need to delete a particular variable which need to be tested. So the reduced model will contain all the independent variable except the variable which you are going to test. And we are comparing these two full model and the reduced model to see whether there is a change in the model performance. To test that, the individual regression coefficient test will be done. And now the null hypothesis will be the coefficient of the regressor, which is being deleted, will be equal to 0. And the alternative hypothesis will be that it won't be equal to 0, which means it is contributing definitely something to the model. Now, since it is only a one variable test, we will go with t-test. And if the t-test value, computed t-test value is greater than the critical value, then we reject the null hypothesis and we prove that there is some effect contributing by this variable to the model. And now, if we see that it is not rejected, that is H not such that beta j is equal to 0. At that case, the regression is no more useful to our model. It is not explaining much to our model. Then we can directly delete that particular regressor from our model. So we'll have the reduced model with us. If not deleted, we have the full model with us. So this is how the testing in multiple linear regression will go. But for our easiness of doing analysis, there are certain variable selection procedures which automate this procedures, what we have done. Like it is not manually easy for us to add each variable, delete each variable and see whether this model is good, another model is good and all. So we have certain automated variable selection procedures. So we have backward selection, forward selection and stepwise selection. So we will deal one by one. So in the backward selection, we start with the process with the full model. That is, it consider all the variables to be included in the model, as you can see in the figure below. So in the 0th step, that is at the first step, initially we have all the variables. So each blue box indicates the independent variables which is being added. So every blue box means the collective information, and if it turns white means it is no more important. So once all the variables have been included in the model and it runs such that if any of the variable is not giving a significant contribution to the model, it will be deleted. So we determine by t statistic and the p-value, and those p-value which has been higher. Like we have 10 variables and among that we have 5 of them significant and 5 of them insignificant. So there arises a question, which insignificant variable should be removed at the first. So those variables which have the highest p-value will be removed first. So next step, as we see in the figure, one of the term with the highest p-value is being removed. Now we have a set of other variables. This process repeats until all the variables in the model become significant. So as we can see that from 0 to step 6, which means it runs 7 iterations to reach to a model in which all the independent variables are being contributing significantly to the y. So at last, we can see that there were 5 variables or 6 variables which were contributing. So even if you add any more or delete any more, like if we delete anything, we are losing some information. If we are adding means we are just like making other model become insignificant. Like we have 5 variables and the 5 variables are strictly contributing to this y, the dependent variable. So this is how the backward selection is being done. So we'll go with the forward selection next. So forward selection means it is just the reverse of the backward selection methods. So it starts with an empty model, null model, which means there is no variable added. And we see how the effect of each variable is being proving to the model significance. So from the 0th step to the first step, one variable is being added. You can see the second figure. So here it is the converse of the backward selection. So whichever term with the lowest p-value. Likewise, in the before case, we have seen like 5 variables was insignificant. So among the 5 variables which have the highest p-value is being removed first. So here we have 5 variables significant in that case which have the lowest p-value. So as the p-value decreases, it is explaining more to the model. So the term with the lowest p-value will be added first to our model, and we see the significance, the performance of that particular variable to the model. And then in the next step, those terms with the next lowest p-value will be added. And this particular process being repeated, iterated such that it gives all the p-value to be significant and no other variables which is having higher p-value will be added. So in the both the cases, we'll have the same variables at the end after the iteration, and all will be significantly contributing to our model. So then what is the stepwise selection? What is happening in the stepwise selection? So in the stepwise selection, they are combining the both forward and the backward selection procedures. So in the stepwise selection, it starts with the forward selection, which means we have the null model first and the variables are added one at a time based on the statistical significance. And once the forward selection is being done, the model again checks whether this significantly adds to the model, and then whenever 2 variables are added, whether the previous variable was significant, whether it has a removal criteria, depending upon that, it do a backward elimination also. So you can understand it clearly by this illustration. So this is what is happening in the forward selection, right? So once we have a null model and the most significant term is added, and then depending upon the threshold or the p-value in which we are able to add the forward processes, we go and add, and we have about 7 iteration, and the process stops until we have a set of significant dependent variables. So how does this backward selection works in this stepwise method? At the 4th step, as you can see, there are 4 variables significant. Okay. Now we have particularly one threshold for removing certain variables. So we can see that the second significant variables is the p-values is greater than particularly the threshold for the removal. In that case, if we are going with the forward selection, it goes on and then it ends up with a particular insignificant variables. And this particular in the 4th step, the second variable is having a threshold for removal. In that case, it removes that particular variable through backward elimination and not through forward elimination. So this will happen iteratively until you have the variables which is significant, which are satisfying both the forward criteria and the backward criteria. So this will be how the multiple linear regression overall works. And we need to assess how this particular model which we have built is good or not. So we have certain information criteria in order to assess these model performance. So that is one is AIC and another one is BIC. So how multiple linear regression overall works. And hello, is there a doubt? Hello.
Hello, we can hear you. It's audible. We can hear you.
Charles, do you have any question?
Hello, we are with you, ma. We can hear you. Hello, we can hear you.
Sir, can I continue?
Yes, Sure. You can continue.
We can hear you, ma. Go ahead.
Okay. So we have two criteria, that is AIC and BIC. So AIC gives us a model quality, like measures the model quality based upon the likelihood of the variables which is being explained. So in simple terms, how we can assess is that we have certain models, like we have in the case of forward, backward, stepwise, we see each iteration. So in each iteration, we see how the AIC or the BIC values varies, and then whichever model is having a lower AIC model, then that model is the best model to be explained. And similarly, the same thing happens for the BIC also. So one thing which is the difference between AIC and BIC is that we can see the formula and we can see what is the difference. So in this AIC model, the equation comes as 2k minus 2ln. So k is the number of parameters, which means intercept plus the slope of every variables will be added up as the number of parameters. And in that case, there does not take sample size into account. What is the sample size of our data? And it does not take up into that. But in BIC, you can see that it takes into account both the sample size and the parameters. So depending upon how large and how small your sample size is, you can use AIC and BIC. So this is how it is being evaluated. And also, like another essential question which will be arising after choosing the variables. So we have a set of 10 variables which has been contributing significantly to the dependent variable, whether they are providing any overlapping information. Say, for example, we include height and we include weight, but combinedly when we are using BMI. So BMI is being computed using height and weight. So both are providing equal information. And if they both are significantly contributing, means their informations are being colliding or overlapping, which should not be happening in a multiple linear regression. So there we have one factor to assess whether any overlapping informations are there in our multiple linear regression. So that is the variation inflation factor. So variation inflation factor means how much variance combinedly the estimated regression coefficients is being provided. That is, it increases if the predictors are being correlated, which means like what I have explained in the BMI height and weight cases. So if they are correlated, means this particular factor is being increasing. So from after a threshold, if this particular VAF value is more, we should remove some variables which are being correlated. And R square, you all know, I think it's been covered in the previous sessions. R square explains how much variance combinedly this particular independent variable is being explained. So in the simple linear regression, when you are seeing an independent variable and the dependent variable, and you are seeing the R square, that is simple R square. That simple R square means how much variance that particular independent variables explains in the Y variable apart from the chance. So that information is provided in the data. Here, when we have multiple regressors, which in the sense we should have the combined effect of all the variables. So we should use adjusted R square instead of the simple R square. And when coming to the VIF factors, if the set of variables which are highly correlated means the VIF might exceed 5, the threshold value we'll see in the practical sessions. And also, if it is, sometimes we set the threshold to 5, sometimes we set the threshold to 10, depending upon the situation. So if it is exceeding this particular threshold, means we need to remove some of the variables. So this will be our data which we will be performing our analysis on in R. Before that, yeah. So here, this question, I will say what is our question and how our data is. And here we need to predict the mean arterial blood pressure based upon the independent variables given. So arterial blood pressure means in the normal range, it is from 80 to 100. And we have the data here. The independent variables is age, weight of the person, body surface area of the person, and how much years the person is having a hypertension, what is the basal pulse rate of this person, and what is the measure of, there is a particular scoring system assigned such that we assess the measure, the stress of the people, and we are combinedly looking upon these independent variables to the dependent variables. Okay, so you can use the, I'll explain this R square also. So this is adjusted R square. So in the simple linear regression, you deals with just simple R squared. So whenever you add a particular regressor variable into the model, say we have 5 variables, and when only one variable is added, you have the simple linear regression itself. So you have the simple R squared. Now you are adding another variable. So you have combinedly 2 variables. Then this R square will literally goes up. So whenever R square is being higher, then the model is getting better. Okay. So if you add another variable, simply the R square will goes up. It is not getting adjusted. So in order to adjust this particular R square, we are using another measure, that is adjusted R square. So the adjusted R square value will only increase if that particular variable is significantly contributing to our model. So whenever we have the highest adjusted R square among the models we have created, we can also assess that this particular model is significantly contributing to our, this model is the better model among whichever models we have fitted. So we can use this particular data to do the analysis for multiple linear regression. Is the screen visible now? Hello.
Yes, ma'am, visible.
I mean, whether the R studio is
No, this is only PPT.
okay. Now,
Yeah, it is visible.
so everyone can use the data which has been already shared, that is the mean ABP data for this particular multiple linear regression analysis. Hope everyone is having the data with you. Shall I proceed? Can anyone respond, please?
Yeah, proceed. We are with you.
Okay. So we have to load these particular 3 packages to do this particular analysis. I hope everyone will be having these packages. These are some common packages. So this particular package is used to load the data. Since it has been XLS format, that is in Excel format, we need to use this particular library to load the data. Okay, so I'll proceed. So we have our data being loaded. Now let's view the data. So this is how our data looks like. So at the first column, we have the mean arterial blood pressure, which is our dependent variable. Then comes age, weight, body surface area, duration of hypertension, basal pulse rate, and measure of stress. So these are the 6 independent variables we will be dealing with in this practical session. Okay, so let's see how our data looks like in a compressed form. So when we use this summary given data as a function, then you will get certain measures for each of the variables. That is, what is the minimum value, what is the first quartile value, what is the median, what is the mean, all those things. So we can see one by one. So here in the mean arterial blood pressure, we can see the mean value of the persons. In our data is 113, which is higher than the normal level. So everyone in the patient history we have with the data, everyone is having more than the normal level. Okay. So once comes to the age variable, we can see that the mean age of person is 48. So everyone is the middle-aged persons, and the mean weight is around 93, and the body surface area, the mean is 1.9, and we can see the people are having hypertension. The average duration of this hypertension is 6.5 years. So in the entire population, we can see that about 6.5 years the people are suffering from hypertension on an average. So similarly, we see the other variables also. So once we need to check for the assumption, that is, we have our dependent variable to be normally distributed. So since our sample size is a little bit low, we can strictly say that whether it is normally distributed. So one way to represent this through a histogram. So I think the plot is visible in the side. So it is somewhat normally distributed. Now we are fitting a model. Okay, as a layman, if you are doing a multiple linear regression, what you will do is like you have a dependent variable and you have a set of independent variables. So you need to combinedly see how each of the variables is explained. So we have a model that is equal to this particular linear model. Multiple linear regression comes under the linear models. So we use LM command, and we have the dependent variable, which is mean arterial blood pressure, and we have a linear combination of the independent variables, which is being given here, and also we provide the information from which the data is being collected. So we use comma data equal to the data name which is mentioned, as you have mentioned. So we'll run the full model. So we need to see the summary of that particular model. Okay. Now here we have the summary. That is, we have the intercept value. This is the beta naught value. And we have each slope values. So this entire set of things will give you the slope value for each of the variables. And this is the t-test value for each variable added on. And then this is the p-value. Okay. So once you see this, say we are taking an example of age. So the estimate is 0.5. So we see that as 1 year age increases, the mean arterial blood pressure of that person increases by 0.5 units. Okay. And we see the p-value has been significant. So the age is contributing to this particular full model. And we can see that the basal pulse rates and the measure of stress is not significant. But still, what happens? As we add all the variables to the model manually, it has been added and the p-value is not significant. So whether this is necessary or not, we need to check. Okay. Now we see the symbol AIC of this particular model using the command AIC model. Clear? Also, we need to check the multicollinearity, which is being explained through the VIF factor. So we are seeing VIF of model. Now you have seen certain variables, values under each variable, that is age, weight, each of the variables are given and some values are being written down under each variable, right? So this is our VIF value. So as you can see that none of the values are greater than 5. So among these 6 variables which we are being using on, there is no much correlation explaining between the variables. Okay. So it is possible to add all the variables if it is significant. Say for example, we have another variable x added on and we have an VIF value which is greater than 5. So in that case, we need to remove any of the particular variables which has been correlated and such that our model which has been built will be better. So we have seen for 3 main variable selection methods. So in this forward model, see, forward model will start with an empty model, which means no variables will be added. Okay. Now, which is the start model? That is, we use an lm command and we use the dependent variable and there is no variable specified. So we use particularly none. That is one. And we use the data. Okay. Now you should run this particular null model and then we should specify our full model also, which includes all the variables in our model. Okay, these are the two extremes, that is the lower and the upper limit in which the variables can be added. Okay, now if we need to perform the forward selection, we use the step command and we say that it should start with the null model. So we also give the scope in which it should start with the null model and it should not exceed the full model. So our model will be in between the null model and the full model. Okay. And there is also one command in which need to specify the direction in which the model should be chosen. So the direction is in forward direction. Okay. So this will be our command for forward selection. So if we run this particular command, we have certain analysis being done here. Okay. So in the forward selection, we have at the start in which we don't have any of the variables. That is, this is the null model. Okay. In that case, the AIC value, as we can see, is at the start is 440. Right. Now you have seen certain variables being listed down here. So you see a none command, none result which is being given, which means that whenever no variable is being added, the AIC value is 440.68. Okay. Now we need to see what has been happening here. Okay. So we see that as we have lower AIC value, it is better the model, right? So here you can see the plus symbol, which means that if we add the particular variable weight to the model, the AIC will be decreased to 281.26. Okay. So in the next step, you can see that the weight is being added, right? So once the weight is being added, you can see our model will have an AIC value of 281. The 440 was reduced to 281. Now, when you can see, if age is being added again to this model, this 281 will be reduced to 212. So, age is also an important factor explained. So, in the next step, the age is being added and you can see that the AIC value is reduced to 212. Now, if again a body surface area is being added to our model, it is again being reduced to 193. So, the body surface area is also being explaining something to our model. So, in the next step, what happens? The body surface area is also being added. Now, our model becomes with an AIC of 193.38. So, if the duration of hypertension is being added, it again reduced to 186. Okay, in the next step, what happens? The duration of hypertension is being also added to our model. Now, what happens here? There is two other variables, that is basal pulse rate and measure of stress. So, it is coming below what our model is specified in the later step. Okay, so what you need to understand from this particular result is that if the basal pulse rate is being added to our model, then the AIC is increasing, which means that this variable is not contributing anything to our model. And if the measure of stress is being added to our model, then AIC is again increasing. So lower the AIC will have the better model. So among this model, whichever model is specified, that is with weight, age, body surface area, and duration of hypertension. So this is explaining much information. So if you add the basal pulse rate or the measure of stress, no information has been contributed. So in the forward selection, it ends up with 4 variables with having a lower AIC value of 186. Okay. So by this you can understand how our full model, like with all the variables, it was explaining a very large AIC. So how this forward selection is running better than our manual model. So similarly, you can see backward selection, how it is being done. So in the backward selection, we start with full model. So you can see the step function here, and we specify it should start with full model and give the direction backward. So it is a simple command. So once you run this particular command, you can see certain things are happening. So here we can see that the mean arterial blood pressure are being related with all the variables. That is our full model. Okay. At that time, the AIC value was 189.32. Okay. So here you can see that in the forward direction, you can see a plus symbol nearby to every variables, right? That is if addition of this particular variable, does it add much to our model? That is what it is meaning. So when it comes to here, it is minus, which means we need to delete. So here when we say that, if we delete this particular measure of stress variable, so this none is our original model. That is what is being specified as the full model. So 189.32 is our AIC. So if the measure of stress is being removed from our model, then the AIC become better. So this is not contributing much. Okay. So in this next step, it has been removed and a new AIC we got. So it is being reduced to 187. So also again, if this basal pulse is being removed, then again the AIC value is decreasing to 186. So this is also not explaining much. So the reverse of forward selection, you can now understand by this particular code and the iterations. And again, that particular variable has also been removed. Now you have 4 variables, that is age, weight, body surface area, and duration of hypertension. So what happens here? So in the full, whichever model is, which means this model. In this model, you have the AIC to be 186.39, which is the AIC which we got in the last model from the forward selection. So what does these 4 AICs indicates? So from this model which is being produced here, if the duration of hypertension is being again removed from our model, then the AIC value is being increasing. So which means that each of these variable is explaining much to our model. This is how it has been interpreted. Okay. Now you see how the backward selection is being done. The full model as we specify in the forward selection also. And what we need to do is in the direction, you should mention it as both. That is in both forward and in the backward direction. So once we run the command, we can see. Okay. So in the null model, as you can see what happens in the forward model, it iterates similarly. Okay. Okay, in the first step, it iterates similarly in the forward selection manner. And when it comes to the second step, you can see a minus and the plus symbol here, right? So the weight is being added. Now the model is thinking whether we should add age or whether what happens if we remove weight. Okay, the weight is being added. So the model now have an AIC value of 281. So if the age is being added, it will be reduced to 212, and if the weight is being removed, it again goes back to 440. Okay, so you see how the model is being iterated. So we add age to the model, and it also gives the AIC value if these particular variables are being removed. So whether it decreases or increases, you can evaluate from the result. Similarly, this particular iteration happens, and we see at last we have again a 4-variable combination explaining correctly to the mean arterial blood pressure. So at last what you see is the model's AIC, that is 186. And you can see that if this particular first 2 variables is being added, the AIC increases. And if any of the variables below that is being removed, the AIC increases. So this is the threshold in which we determine whether to add a variable or whether to remove the variable. So this is what we have been discussing in the multiple linear regression. I hope everything is being understood from this particular code and how these particular model selections works. Okay, now we'll go with the next topic.
So, ma'am, for any multiple regression analysis, means how can we select that? Should we go for forward or backward or stepwise? Means is there any conditions laid there, or we have to check all the 3 selections?
Actually, forward, you see how we can visualize how each variables contribute to our model. So once you are being doing it stepwise selection, like it combines both the forward and the backward selection. So
Yes.
once a variable is being added, and what happens if that particular variable is removed from the model in between, you can see, right? So stepwise will be most preferred over the 2.
Okay. Okay.
Yeah.
Okay. Thank you.
Is it clear, like how you can visualize the importance of each variable?
Okay, ma'am. Thank you.
Thank you. So can I move forward to the next topic?
Yes. Yes, ma'am.
Is the screen visible now?
Yes, it is visible.
So we have been dealing with a variable which was in continuous nature. So what was the effect of these independent variables to the dependent variable? So we see the unit change, how the mean dependent variable is changing with respect to the independent variables. So we need to move forward a little bit and see what if the variable is categorical, which means what if our dependent variable is categorical. So I will see certain situations of this particular problem. So, for example, if a person arrives at an emergency room with a certain symptoms, so there should be 2 medical conditions. Say the doctor is having 2 medical conditions. So, depending upon the set of symptoms, which condition does this individual have? This cannot be in a continuous manner, right? So, another condition, that is if a biologist collects the DNA sequence data of a number of patients for a given disease. So our variable becomes whether the person is having a disease or not having the disease. So which DNA sequence or mutation are causing this particular disease? In that case is also the dependent variable becomes binary. That is whether the person has the disease or does not has the disease becomes our point of question. So in that case, we move to our next regression method, that is logistic regression. So it is used to study the association between a dependent variable, which will be binary in nature, and an explanatory variable, which can be any kind. It can be categorical or continuous nature. So there are 2 types of logistic regression, that is binary models, which will have a dichotomous outcome. That is 2 outcomes. Yes, no, positive, negative. So like that. And there is another model, that is multinomial models, which will have many categories to our dependent variables. So here in this session, we will be only dealing with binary models. So what is the theory behind this binary logistic regression? Say our probability of success at any x means the independent variables, So what is the probability of success, or the number of yes, the proportion of yeses, the proportion of ones, the proportion of success at any x? It is being denoted by pi. Okay. So we will deal with the equivalent forms of the logistic regression model. So what is logic? What is logistic? Which we need to know. So we have the log of the odds. The odds is being represented by the pi divided by 1 minus pi, which is nothing but the probability of success divided by the probability of failure. And if we are taking that particular measure to the logarithm, we have the logic function. Okay. So this particular logit of success or the logit of odds is the linear combination of the independent variables. So in the multiple linear regression, you simply write y equal to beta naught plus beta 1 x1, beta 2 x2, etc. up to beta n xn. Similarly, we'll have our RHS, that is the right hand side, to be in the similar format. Only change happens in the left hand side. The dependent variable, the mode of dependent variables changes to the logic function, that is the log of odds. So once we are having the probability form, okay, of this logistic regression, we have the proportion of success to be which is displayed in the next in the right, that is we are taking the exponential of the linear combination and we are dividing. Okay, so I'll explain it with an example. So to predict the probability of getting CVD, that is cardiovascular disease, or it is being denoted by y, that is the dependent variable, and we have hypertension as the independent variable. Okay, the hypertension is yes or no. So we have an estimated probability here. As I have displayed above, we have substituted certain values to it. So here the beta naught is 64 and the beta 1 is minus 0.9. Okay. So if the person is having hypertension, what is the chance of getting cardiovascular disease, that is CVD, can be estimated through this particular regression. So if we have the hypertension, yes, and the probability is estimated to be about 0.72. So here what it is meaning is that if the person is been suffering from hypertension, then the probability of getting CVD for that particular person is 0.72. That is 78% of the people who are suffering from this particular hypertension will have a chance of getting CVD. So what is this odds or odds ratio? We need to know, because it is how the logistic regression will be being interpreted. So once we are seeing the definition of odds, okay, as I have said that it is the probability of success divided by the probability of failure. And we can also estimate the predicted probability of a person using the odds also, which is being displayed here as pi equal to odds divided by 1 plus odds. Okay. Now we see that in the logistic model, it assumes to be a linear relationship between the predictors and the dependent variable. Only once if the logistic function is being induced into the model. Okay, so the logit is the linear combination of the variables. Now you can know how the odds can be represented, right? So if we are exponenting the equation, the first equation given, and if we are exponenting means you get the odds. And if we are taking the ratio of two odds, it becomes an odds ratio. So we'll have an odds of a person having yes and odds of the person having no. And we are comparing these two particular odds and see how that variable is being explaining to our dependent variable, whether that particular independent variable will be increasing the chance of getting this particular disease or decreasing the chance of getting that particular disease can be interpreted using this odds ratio. Okay. So here we will be dealing with an example, like let's see an example here. So the question is the probability of normal birth weight of a child who is born is associated with the gestational age of the mother. Okay. So we have a descriptive statistic table which is displayed in the left, right. That is, we have in the total 24 babies who are born, we have 17 of them with normal birth weight and 7 of them with the low birth weight, which means 70% or 71% of the babies who are born as having normal birth weight. And we need to see whether this gestational age is having certain effect of to have a baby born with a normal birth weight. Okay. So our response variable becomes, that is the dependent variable become the birth weight, in which 1 is being coded as normal, 0 is being coded as low. And the explanatory variable, which is the gestational age given in weeks. Okay. So once we have fitted the binary regression models, we get it as log of pi, that is log of odds, is equal to, we have an intercept value, that is minus 48.9 plus 1.31 gestational age. Okay. So what does this 1.31 signifies? Okay. So we have 2 cases of interpretations here. So we have 1.31. First we will interpret 1.31. So as 1 week increase in the gestational age, then the log of odds, okay, of a normal birth weight increases by 1.31. Okay, but is it really possible for a person to understand how this particular variable is being contributing to the normal birth weight? Like, if you are explaining this problem to a particular layman, saying that if the gestational age is increasing by 1 week, then the log of odds is being increased by 1.31, has not been a proper way of interpretation, like proper way of understanding. So we change the interpretation in terms of odds, okay, which means we exponent that particular coefficient. That is, we take the exponential of 1.31 and we get it as 3.71, sorry. Okay, so we interpret this particular coefficient as 1 week increase in the gestational age multiplies the odds of having a baby with a normal birth weight by 3.71. Okay, so it increases the chance as the gestational age increases, then the chance of getting a normal birth weight baby is being increased by 3.71, which will be a more proper way, more understandable way for interpreting this particular logistic regression. Okay. Now we can say see how this particular model is being evaluated. So one such way of our model being evaluated is through a receiver operating characteristic curve, that is an ROC curve. So this ROC curve will give you how the model performs, as we see later as AIC value and adjusted R-square value and the multiple linear regression. Here we are having the receiver operating characteristic curve, and this curve is being plotted between the sensitivity against the 1 minus specificity. So let me explain what sensitivity and specificity is. So we have an outcome variable, among which in this case we see the low birth weight and the normal birth weight. So normal birth weight are our area of interest. Okay, so in that case we have 100 babies with 56 of them having normal birth weight. So we have fitted a model and we have a predicted probabilities extracted from it. And depending upon the predicted probabilities we have extracted, how good this particular model predicts the baby to have the normal birth weight, the baby to have the low birth weight. So among the predicted cases, like we'll have an actual outcome and we'll have a predicted outcome. So among this, if the how much percentage of our babies are being correctly predicted among the true. So that proportion is explained using the value of sensitivity, and specificity is the reverse case, which means among the low birth weight babies, how much babies are correctly being identified as low birth weight gives the sensitivity. So this plot is actually a trade-off between the sensitivity as well as the specificity. Okay. So you can see that and the area under this particular curve. The curve is being drawn between each of the values, and if we see the area under each curve, that is how the model is being evaluated. As the area under the curve increases, the predictive ability or the classifying ability of this particular logistic regression is being increased. So it have a range. Okay, so the range is being from 0 to 1. But practically, when we are seeing, the lower limit is being set to 0.5. So if you fit a model and that particular model is having greater than 0.5, means somewhat the model, if it is equal to 0.5 or somewhat little higher than 0.5, means this model is capable of classifying. But how much capable this model is to be identified using this AUC. So as the AUC value approaches to 1, means it is being perfectly classified or being perfectly predicted. So you see 3 curves being drawn in the figure. Okay, so the one which is nearer to the axis is having a perfect classification with the AUC of 1, and again you have an curve with an AUC of 0.92. Okay, it is somewhat little bit lower than 1. So there is something happening in the model which is allowing it to have a decreased AUC value. And similarly, you have another AUC value below that, that is with the AUC of 0.7. Okay, so depending how much AUC we get at the end, that is in the last model. After we'll have the practical session, you'll get to know how the variables are being added and how the model is being chosen. So at the final model, how much does this particular model gives? What is the predictive ability of the model is being explained through the ROC curve. Okay, so we can see and understand through the practical session. So is this visible, our studio? Hello. Hello.
Yes, ma'am.
Yes, it is visible. Yeah.
So in order to do this binary logistic regression, we need to have these certain libraries to be installed. Do everyone have this library, or should I paste it in the chat box? I'll do one thing. I'll just give you the entire code. You can So I have pasted some of the codes into it. Like there is a limit to send the message and all. So it will be helpful for you to easily do the analysis. So you have to run all the libraries for this particular session. And you have to import your data. I hope everyone have done this particular step right now. Okay. Now let's proceed. So let's view the data. Okay, the first one is the unique identifier number, that is serial number. We don't need to care about it. So the next one is gender. So one is being coded as like male is being coded as 1, female is being coded as 0. We have the age in years. So the entire data is about dementia. So whether the person will be demented or non-demented will be our outcome variable. Okay. So the demented will be the 1, non-demented will be the 0. So these are certain variables like E, T, I, V. And the 3 variables is something related to dementia. So that is estimated total intracranial volume. Second one is the whole brain volume. And another one is certain score, that is the mini mental state examination scores. So these are the variables which will be related to the dementia factor. So we are seeing how these variables are being associated with our outcome, whether we are able to predict a person is having dementia or he is being demented due to these factors or being non-demented. Okay. So unlike the other multiple linear regression, we have here the categorical variables, right? So the outcome variable will be categorical, gender variable will be categorical. So the R doesn't know whether the variable is categorical or whether the variable is continuous. In that case, we need to let the R know that this particular variable is categorical. For that, we convert it to factors, that is the categorical variables. So the gender is being converted to factor using the code as dot function. Okay. Now the gender is being categorical and the outcome is also being categorical. So this step should be done at the first itself. So whichever categorical variables you have with you should be coded at the first as categorical, and then only you should do the summary of the data. Okay. Now let's see the summary. So we can see that in the total population, there is 139 males and 208 females. And also among the total outcome, we can see that 157 people is having demented and 190 people are being non-demented. Okay. And we can see the mean age is being 76, which is we are dealing with a very older population. So there are certain mean values for this clinical parameters also. And the mini mental state examination, the mean score is about 27.47. Okay. So this is how our data distribution is like. So we can see how the distribution of each variable, each continuous variable is being. So we plot a histogram for age, it is being somewhat normally distributed. For the other variable, it is also normally distributed. Okay. So the other variables are gender. So we are not taking up for seeing the distribution pattern. Now see how each of the continuous variables are being correlated before doing the logistic regression analysis. So we use this particular COR for the correlation, and we select only the variables age, these 3 parameters, clinical parameters, and when we run the correlation, we can see that how each variable is correlated with the other, and we see only between the normalized brain volume, that is normalized whole brain volume, is being little bit associated with the age. So it is being given that as the age increases, this particular value is being decreasing. Okay. Does this factor correctly contribute to our logistic regression or not? We can see. So once we are doing a logistic regression, so before adding all the variables like multiple linear regression to a model, we should correctly identify each variable which are contributing to our model. Okay. So we need to see how each variable contributes the outcome at the first, and then only we will move forward to the multivariable logistic regression model. Okay. So at first we need to run the univariate logistic regression. So In the multiple linear regression, you have been seeing LM only. So once you come to this particular logistic regression, this is being changed to GLM. GLM means generalized linear models. Okay, logistic regression and all other extensive modeling comes under GLM. So we have the similar code of being done, which we've been dealing with in linear regression. Okay, so what happens here? We have the outcome variable and how it is associated with age is our first priority. Okay, and we provide the data and we give a certain new information to this particular model. What is that? That is whether which family do this outcome variable belongs. Okay, so in multiple linear regression, we do not have to specify it it consider it to be a linear and a normal distribution. So we did not want to correctly mention it. So here we need to mention, because general linear models contains an extensive family of distributions. So here we have a binary model. So we use the family to be a binomial distribution. So we have mentioned binomial here. And if we run this particular model and when we get the summary of this model, okay, so what happens? So here you can see an intercept and also the estimate of the age. Okay, so whatever estimate which is being provided here is in terms of log odds, okay, not in terms of odds ratio, and the probability is being given here. So the Z value, like as we see the t test and f test in the linear regression, here the Z value, the walt test is being running on. Okay, so you have this age and an estimate. So you should explain like just completely ignore the p value, and if you deal with the estimates, how we will interpret it is like, as age increases by 1 year, the log odds of getting dementia or being demented is decreasing, which means it is in negative, okay, in the log odds terms, okay. But in the log odds, it is not easier for us to interpret. So we use the exponential factor. So we exponent, that is, this code will be exponent the coefficient of this model. Okay. Once we exponent, we have this particular value. Okay, this is now in odds ratio. Okay, so here we have 0.99. So once the odds ratio, we are taking the ratio means the null value will be 1. So if the odds is greater than 1, then it is more riskier to have that particular factor associated with the outcome variable. So if the odds is less than 1 means it is acting a little bit as a protective factor. Okay, so this is how the age has been contributed. So once we interpret this particular 0.99, then we say that as age increases by 1 year, the odds of getting this particular dementia or being demented is being less chance. That is, we subtract this particular odds value from 1 and we interpret if it is less than 1. If it is greater than 1 means we can directly interpret that particular value. So if it is less than 1 means we subtract this particular value from 1, and here it is will be 0.01. Okay, and at that case it will be 0.01, which is not much a very big chance of getting protective, because maybe due to the data constraints, due to the sample size, this has been giving an estimate of this. So if we have a larger sample size of a correct measurements of without error, if it is being measured and all, we can maybe see as age increases, the person getting demented or dementia is being increasing, the chances will be increasing. So it is likely to be nearer to 1. So we couldn't clearly give an interpretation that this is a protective factor or neither a risk factor. Okay. So once we are dealing with gender, we can see similarly. So the odds is 2.08. So here you can clearly get that here it is given as gender 1, which means that with respect to, we are giving female as our reference category. So When compared with females, the males have 2.08 higher odds of getting dementia. That is how the odds ratio will be interpreted. In this case, it will be clearer for you how this particular odds ratio works. And you can see that the p-value is being significant here. From the model summary, you can see how each variables contribute significantly or not. But if you are dealing with the medical research, like age and gender, somewhat may not be contributing well to our model. Maybe it will be significant, maybe it won't be significant. But it depends. Like many of the times, the age and gender will have a crucial role. Maybe our data won't be supporting to that. In that case, also we'll add this particular variable manually, even if it is not significant. Okay, here the gender is exhibiting a very high significance. So we can see the next model. In the next model, this particular total intracranial volume is not explaining much. Okay, the p-value is not significant. And you can see the odds is nearer to 1 also. So similarly, we have all the variables to be done in this particular univariate manner. Okay. So once you deal with the whole brain volume, you can see that this particular variable is highly significant. Okay. This is highly significant and the odds is very low. So as the intracranial volume increases, okay, the whole brain volume increases, then you can see that the odds of getting the dementia reduces to a very large amount. Okay, this is how the interpretation will be get on. So this value, like it is very, very low. So once you subtract, we can see that the risk is very low for this particular variable. Similarly, you can see for the next variable, that is mini mental state examination. So here also the odds is around 0.4, which means that the person who is having higher mini mental state examination scores is likely to have less chance of getting demented. So it is also scientifically proven that if the mini mental score is higher, the chances of getting dementia is lower. Okay, the dementia will be in the lower amount. So it is around 60% or 0.6 times less odds of getting this particular disease. So this is how the univariate logistic regression will be iteratively done for each variables, and from the univariate logistic regression, you get to know which all variables are significantly contributing, like independently significantly contributing to the dependent variables. So after that, you need to know the person will be having this multiple factors together. So likewise, we have dealing with simple linear regression and multiple linear regression. Here you will be dealing with what univariate logistic regression and collectively in the multivariate logistic regression. So in the medical or clinical scenario, some variables which is having clinical significance, even if it is not significant in the univariate regression, we will add it manually to the multiple logistic regression. And all those variables which has been significantly contributing in the univariate logistic regression will also be added on. Okay. So here, except the total intracranial volume, that is ETIV, all other variables except age and ETIV, we are adding all the variables. But due to the medical significance, the age has been already added because it has been proven that as age increases, the chances of getting dementia also increases. So I have added that manually, and all other variables which has been significant in the univariate logistic regression is added. So it is also a linear combination, right? So we have given the GLM code, the outcome, and the linear combination of the independent variables. We have specified the data and also the family to which it belongs. So this becomes our final logistic regression model. Okay. Now, when we run this particular command, okay, and we need to get the summary of this particular logistic regression model. Okay, so this is how our model looks like after adjustments. Okay, So in order to estimate this particular odds ratio, we took the exponential, and you get to see each of the odds ratio of variables. So we have odds ratio for gender, odds ratio for age, odds ratio for normalized whole brain volume, and the mean mental state examination. So you can see that in the univariate logistic regression, the odds ratio of gender was about 2.08 times, right? So after that, once you have clubbed all the variables to the multiple logistic regression model, this has been adjusted. So this is the adjusted odds ratio, not mere the simple odds ratio. So the term changes to adjusted odds ratio, and you can see that it reduces to 1.3. Okay, so this is how each of the odds ratio will change collectively when other factors are acting upon the dependent variables. Okay, so in this case, we interpret that assuming all other variables, that is age, normalized the whole brain volume, mini mental state examination results, keeping all other variables to be constant, how the gender contributes to the proportion of getting dementia. So here we interpret it as compared to females. Females is being reference category, and as compared to females, the males will be having 1.3 times higher odds of getting dementia when the age, normalized whole brain volume, mini mental state examinations are keeping constant. Okay, similarly, we'll explain for age, we'll explain for the other variables. So gender, since it is a categorical variable, we need to provide the reference category, and the interpretation should be done from this reference category. And in the continuous variables, we interpret as an year increase or an unit increase. Like for weight, we say 1 kg increase. So whatever unit that particular variable is mentioned on, with respect to that, a 1 unit increases, keeping all other variables constant. How does this explain to the dependent variables? How does the proportion changes in the dependent variable is explained in this logistic regression. So also we see that in this particular estimates value, the gender is being insignificant when it is being adjusted also. And the age, other variables are also becoming significant in the multiple logistic regression. So when you are dealing with practical cases with more variables, you can also see that in the univariate logistic regression, some variables may be significant, but after that, when you are adjusting for other variables, so that variable can be insignificant due to certain other factors depending on the dependent variables. That cases are also possible. And you need to know what is the confidence interval of these particular odds ratios. So we use this particular command for getting the confidence interval of each variable. So you can also see certain warning messages popping out. So this is because due to our data and due to the values of certain independent variables, we are getting the predicted probability from the model to be likely to be 0 and 1. But in practical scenarios, it has not been happened. It won't be happening. Like in the sense here, our data is having only a certain subset is being given from the whole data. So there is certain chances of getting the predicted probability from the model to be 0 and 1. That is why this error is being, or the warning is being popping out. And we are seeing the confidence interval. So once you are seeing the confidence interval also, so you can estimate this will be the 95% confidence interval being displayed out for each of the variable. So you can also see how the range of the variable has been range of each odds ratio for each variable has been given here. So you can also identify the significance of each variable from this particular confidence interval also. So if the odds ratio's null value is what? 1. So if 1 is being included in between this 95% confidence interval also, we can directly say that this particular variable is insignificant. So whichever confidence interval is not having a null value will be what statistically significant. So you can get to know it by this particular gender itself. So once you are seeing the gender, it is from 0.7 to 2.39. Okay, and our point estimate, which we get from the logistic regression, was about what was it? About 1.33. Okay, so the range is from 0.7 to 2.39 with having a point estimate to be 1.33. So the one is being included in between that interval, and we say that it is not statistically significant. So you can also see the variation of the data using this confidence interval after the logistic regression, how wider the confidence interval is, how narrow the confidence interval is. So it directly depends upon our sample size also. The sample size is very low, the confidence interval becomes more wider. The sample size is very large, means the confidence interval will be narrower if the standard error is very less. Okay. So these are certain things which you can be seeing. And another thing is that now we have built a model. So we need to assess how this model behaves, right? So in order to assess, we need to first calculate the predicted probabilities of the each particular individual's predicted probability from the model depending upon these characteristics. So in order to get the predicted probability, we use this command. And here I am using data dollar predicted probability. So indirectly, this particular predicted probability will be added upon to the data. Okay, so I use the predict command to get the predicted probabilities, and I use the final logistic model, and I specify the data, and I give the type as response. Okay. So once I run this command, you can view the data now. So once you view the data, you can see that the predicted probabilities is appearing as an other variable in the data. So here you can see that the predicted probability of each individual. Okay. So here you can see the predicted probability to be 0.7. Here you can see the predicted probability to 0.18. Okay. So for each individual, the predicted probabilities here are being given here. So depending upon this predicted probabilities, we are seeing how our model is. Okay. So we use, as I have mentioned about the ROC curve, you can see here the data outcome. So this ROC, particularly this ROC package is PROC package. Okay. And the ROC command will be got it from this PROC. Okay. So we give two particular inputs to get the ROC curve. So first one is our observed value. That is the data dollar outcome. Outcome is our observed value. And next one is data dollar predicted probabilities, what we have estimated in the before step. Okay. Now we have these two values, and depending upon these two values, the ROC is being plotted. So the ROC curve function has been executed, and we need to know like the model performance is being assessed from the AUC, that is the area under this ROC curve. So we use AUC function to get the area under the ROC curve, and once we run it, we get that the area under the curve for this particular model is 0.86, which means that it was nearer to 1. Okay, so these particular independent variables which we have contributed to the dependent variable is explaining a larger amount of variance in the dependent variable. Also, this model is performing a better to classify this particular patients with dementia and non-dementia. Okay, now you can see how the curve is using the function plot, and you put this particular values of the ROC curve, and you give the title, and also we give the color of the curve to be blue. Okay, so you have this particular plot which is being plotted out, and you have sensitivity and you have specificity. So in the slide which I have mentioned, they have used 1 minus specificity. The 1 minus specificity means the axis just gets inverted. Okay, so it will be from 0 to 1. Here I have used specificity, so it will be from 1 to 0. Okay, both are same. So you have plotted sensitivity and specificity, and you get the curve, and it is approaching a little bit nearer to the axis with an area under curve of 0.86. So this is explaining much. Okay. Also, you can use certain models to evaluate this particular area under the curve. You can assess how the area under curve changes with different combination of variables, or you can add more variables and see how the area under curve changes. It's all up to you to explore all those things and all. So this is how, as a scratch, we can do multiple logistic regression and multiple linear regression also. So I think everything will be clear by now about this data. So
Dear participant, the session is for open discussion.
Yeah.
If you have
thank you
any
for
question,
listening to all the content, and if you have any questions or any doubts regarding this particular modeling and all, you can contact me through this email mentioned in the slide for any other doubts, clarifications, anything. Or if you have any clarification regarding the session which is being done now, you can ask the questions.
yes, please, you can unmute your mic and ask your query. Dr. Pooja, Sima Mandal, anyone, please, if you have any question. Elena. Ma'am, Himanshu is asking in the chat box, please check it.
Okay. Like, what is there any assumption for binary logistic regression? So, like what we have discussed in the multiple linear regression, also all the similar assumption has been carried out in the binary logistic regression. Also, there should not be any multicollinearity. There should not be like any outliers. There should be a logic linearly, as we have seen that in the linear regression, the combination of this independent variable should have a linear relationship with the dependent variable. So in this case, the linear relationship should be changed to logic linearity. And also, there should be an existence and independence of variables. Is that clear?
Nidhi Patel. Elena, yes, all the document which we present during the session will be provided to you.
Yeah. I'll share the codes and the PPT with you for further reference.
Dr. Bisuddeep, any question, please? Ma'am, there is one more question, AIC or BIC, which one is best?
Okay, so both the information criteria can be used, but depending upon the sample size, it relies to choose between AIC or BIC. So whether the sample size is large or small depends on how the BIC values will be chosen, but likely it has been used to have the AIC for larger samples.
Okay. Dear participant, if you have any question, please feel free to ask. The session is now open for the discussion. Ma'am, there is one question from his side. Some of are using R-programming and some are using Python. So if we compare these two both, which one is best for the data analytic in for biostatistics?
As far as I know, I am not that experienced to be in Python.
Okay.
So I have used a little bit of Python for certain analysis only, so I couldn't clearly mention, but R has been most widely used, I think, for the statistical purpose as of now. I'll recommend R.
I think there is no more question from the participant. And thank you, dear participant, for your participation in this session. And thank you, ma'am, to deliver your valuable content associated with the advanced regression technique. And during this session, you cover multiple regression analysis, logistic regression for, and model evaluation and validation techniques. There is one more question, normality assumption from Himanshu. Himanshu, you can unmute your mic to put your question. Histogram, it is not, it is unclear. Okay.
So depending upon the sample size, you can rely on two tests for normality assumption. That is, one is Shapiro-Wilk and another one is Kolmogorov-Smirnov. So depending upon that, you can test the assumption of normality and you can see the p-value. Yeah, you can use both the QQ plot and histogram. So just for the layman understanding, I have used histogram.
Okay, thank you. If anyone have more question, please feel free to ask. Okay. Thank you to all. So now it is time to over the session. Ma'am, thank you very much for your valuable time and all the questions as well as the way of your presentation is very nice, and I hope that the content which you deliver will be very helpful, informative, knowledgeable to all the participants. I think today is, as we know, Janmashtami and less participant we can see today. Indians are enjoying this festival, and happy Janmashtami to all also. The presented content will be provided to all the participants and will be uploaded in the Google Drive. The link has been already shared. So after some time, you can check Google Drive link. Okay. So ma'am, once again, thank you very much for your time. And good night.
Thank you, sir, for inviting me to this particular workshop. And thank you all the participants for joining and listening to me. So if you have any further queries, you can also mail me. So I'll provide the suggestions.
Yes, participant, you can directly contact to email address is there. If you have any question, any problem in the future, also you can collaborate and you can contact Geethu Pal. She will help you for your findings, for your problems which you are doing. So thank you very much. Now, good night, and tomorrow we will join the session at the same time. Thank you.